Can we just restart? Oh my god.
It's okay, come on.
I'm sorry. It's been such a long day.
It's recording.
I've been...
It's recording.
Okay,
You cannot edit it out.
Yeah, I know. Brian should. All right, so good afternoon, everyone. My name is Jonathon Savoy. I am a chemical engineering student here at the University of Alabama, Huntsville, and my unit operations group last semester worked on the countercurrent heat exchanger. So the chemical engineering application of a heat exchanger, that's the product that we're going to talk about. So we need to understand the theory, how to model a heat exchanger, and the actual application. So the modeling equation that lets us understand the dynamics within a heat exchanger. So the actual application, talking about, so like modeling an industrial process is vital to chemical engineering. If you don't have an accurate model of what an operation is doing, if there's any type of perturbation to the operation, you'll have no idea what may happen to the system. So the assumptions we made for this heat exchanger, we assume the system is insulated and ideal in that all the heat lost by the hot fluid is directly gained by the cold fluid through a set of thermal resistors. So there's barriers to heat transfer in this system that we're taking into account. And so no heat is generated due to potential viscous flow. So there's no heat generation due to drag on the tube walls. So here's our flow sheet. Brian, Peter, and Will had talked to you guys in the lab about our hot water heater that is allowing hot water to go into our heat exchanger here on the tube side, and the cold water coming in on the shell side, and they're going counter-currently, so they're going in opposite directions. So as we said, here's our heat exchanger system. Tubes 1 and 3 are the tube side and the shell side inlets. 2 and 4 are the tube side and shell side outlets. So we see that they're coming in on separate sides and passing through each other counter-currently. So a little bit of the theory of the heat transfer that's going on in this system. It's important to note that heat always travels from hot to cold. That is thermodynamics like 101. Like, you have to understand that principle. And so as we said, this is a countercurrent heat exchanger. So the hot tube side is coming in this direction, and the cold is coming in the opposite direction. These two Q equations are used to find an experimental heat transfer for the system, and the Q1 is used to for the design heat transfer that we have. So in both equations, we can relate the Q's in order to understand the movement of heat in our system. So these are the definition of variables that we used. You have to take into account all of the thermal and the fluid viscous properties in order to model this heat exchanger system. So foundation equations, you begin with area, flow, and tube side velocities, and just overall diameter of our coil system. And we have to take into account the length that the fluid must travel in this system in order to better understand the fluid properties. So here are our governing equations. Now all 4 of these numbers are dimensionless. They relate fluid dynamic forces to heat transfer coefficient. So the Reynolds number is allows you to understand how turbulent your flow is. Now in our coil heat exchanger, the transition state from laminar to turbulent is going to be a little bit higher than if it were just a simple straight pipe. That number is modeled with the transition state, which we know there's stabilization forces within the tube that allow it to stay laminar for longer periods. Now the Prandtl number and the Nusselt number are correlations that allow you to model like heat transfer or heat flow in the system. So using all of the previous equations, we find the theoretical overall heat transfer coefficient, and we compare it to the experimental heat transfer coefficient. So in all of these terms right here, you'll see them better on your PDF. So they're essentially just resistances to heat flow. So this first term is resistance to heat flow on the shell side, and then followed by the resistance to heat flow on the tube side. And we took into account the copper, which allowed us to model that resistance, as well as the scale factor that may be in the system. And so by equating Q1 and Q2 on slide 3, we find that the experimental U-naught is expressed with this equation. So here is the results of our modeling. We find the theoretical, which are the solid lines, are what we found here, and the modeling equation are these 2 dotted lines here, which we show that they're actually pretty close, a good simulation as we found. So these are the numbers that we used to plot those data over there. The average percent difference is around 11%, and so the correlation equations with this model were pretty accurate overall. So a few conclusions. We found that the overall heat transfer coefficient was a strong function of velocity. So the higher the flow rates, the more likely the flows were to be turbulent, and you have a greater amount of heat transfer. Further, in all cases, the experimental U-naught was less than theoretical. This is because the system could have had some excess fouling, or the flow rates weren't exactly tuned, And so like there was going to be a slight difference in correlated data there. And so finally, a few closing remarks. The modeling of the system really allows us to better understand the system dynamics. So we could, at this point, have changed the flow rates from 1 and 5 gallons a minute to, say, 2 and 10 gallons a minute, and had a better idea of what the driving force or what the temperature difference would have been, now that we have an accurate model. And so this experiment was done in Chemical Engineering 440, which was unit operations. This is really a capstone design lab. So we're combining all of the fundamental ideas from our early engineering classes and science classes and really putting them all together. This was a really eye-opening experience for our design group, and it really, we were given 3 weeks to, get an introduction to a system and then design the experiment and finally model the equations. And overall, it was pretty accurate and a successful experiment.